Local LLM Infrastructure and Optimization. The promise of running large language models on commodity hardware has always hinged on one brutal constraint. How many bits per parameter can you shave off before the model forgets how to think? Microsoft's bitnet.cpp pushes that question to its logical extreme. Ternary quantization, where every weight is encoded as -1, 0, or +1. The inference framework, now over a year old, supports a growing roster of models including bitnet B1582B 4T, a Llama 3 variant adapted to 1.58-bit quantization at 8B parameters, and several Falcon 3 instruction-tuned models ranging from 1B to 10B parameters, all available on Hugging Face in optimized GGU format. The technology is elegant. The adoption is nearly non-existent. The local Llama community's reaction tells the whole story. A textbook chicken and egg problem. Neither CPUs nor GPUs are architecturally optimized for ternary arithmetic. They can run the computations, but they do so inefficiently, negating much of the theoretical advantage. Custom silicon could make 1-bit inference genuinely competitive, but no chipmaker will invest in specialized hardware without a proven ecosystem of high-quality models, and no one will train high-quality models without hardware that makes them worth running. As one commenter put it, it's not the idea that's bad, it's that today's CPUs, GPUs were never designed for this workload. Microsoft, despite having the resources to build a hardware prototype demonstrating real-world performance, has evidently decided to allocate capital elsewhere. The result is a technically fascinating framework sitting largely unused, a reminder that in the local LLM space, a good architecture without a viable hardware story is just an interesting GitHub repo. Meanwhile, the practical concerns of running LLMs in business contexts continue to generate real tooling. An Australian developer has built a self-hosted API proxy that strips personally identifiable information, tax file numbers, Medicare details, passport IDs, credit card numbers, before prompts reach any model, whether cloud-hosted or running locally through Llama or LM Studio. The proxy uses a hybrid approach of fast regex for structured Australian PII patterns and lighter contextual analysis for free-form data, like names appearing near medical terms, adding roughly 2 to 3 milliseconds of latency per request. It deploys as a single Docker container and maintains an immutable audit trail for compliance. The tool highlights a gap in the local model ecosystem. Most privacy and compliance tooling assumes you're using OpenAI's API, leaving the self-hosted crowd to fend for themselves. The local and open-source multimodal landscape is also maturing rapidly. MiniCPM-o 4.5, a 9B parameter model designed to run entirely on device, reportedly beats GPT-4o on vision benchmarks while supporting real-time bilingual voice conversations with no cloud dependency. NVIDIA's Nemotron Embed v2 family of visual document retrieval models, 3B, 8B, tops the Vidore v3 benchmark by 3%, purpose-built for extracting information from scanned documents. And Metafair's Tiny LoRa method pushes fine-tuning efficiency to an almost absurd extreme, enabling model customization with as few as one trainable parameter, effectively dropping the compute barrier to near zero. These developments collectively paint a picture of an ecosystem where the models themselves are increasingly capable and efficient. It's the infrastructure around them, hardware support, compliance tooling, deployment automation, that remains the real bottleneck. AI agent development and system architecture. If there is a single lesson the agent building community keeps relearning, it is this. Prompts are probabilistic, and probability is just a polished synonym for it will eventually break. A post gaining traction on local Llama articulates the problem with unusual clarity. When you build an agent around a 7B or 8B model, running under aggressive 4-bit quantization or extended context windows, the model's adherence to rules encoded in a 2,000-word system prompt will degrade. Not might, will. The proposed solution is what the author calls a logic floor, a deterministic schema layer that wraps inference using constrained output techniques like GBNF grammars, a grammar format used by llama.cpp to restrict token generation to valid patterns, JSON schema validation, or structured generation libraries like guidance and outlines. The model handles the intelligence, the code enforces the logic. The claimed result is zero hallucinations on safety-critical values, 100% SOP adherence, and actually lower latency because the model no longer wastes tokens thinking about rules the schema already enforces. This architectural pattern, splitting probabilistic reasoning from deterministic validation, resonates with a broader intellectual thread. Raphael Nuth's editorial analysis collides the popular brain OS concept, exemplified by Tiago Forte's Building a Second Brain, with the discipline of building an actual software operating system from scratch. The key insight: real operating systems are deterministic, same inputs, same outputs. Memory is protected, processes are isolated, interrupt handling follows strict protocols. The personal operating system metaphor, Nuth argues, collapses under scrutiny precisely because it lacks these guarantees. But the analysis goes further, advancing a provocative hypothesis. Every artifact of knowledge work is de facto becoming software. SOPs, compliance documents, sales playbooks, these are increasingly consumed and acted upon by agentic AI systems, which means they need the same rigor as code: clean architecture, test-driven development, CI/CD pipelines. Whether or not one accepts the full thesis, the core observation is sound. As agents gain autonomy, the gap between document and executable specification narrows to nothing. The tooling ecosystem around agent development is evolving to match these architectural demands. Entire.io has introduced a session capture system for AI coding agents that records every prompt, response, file modification, and token count, creating rewindable checkpoints with 12-character hex IDs. It supports two strategies: commit-based capture for clean Git histories and auto-capture after each agent response for maximum granularity, storing everything on special shadow branches that don't pollute working code. The tool reflects a growing recognition that when agents write code, the provenance chain, who decided what, when, and why, becomes as important as the code itself. An MCP, Model Context Protocol server designed to synchronize context across Cursor, Claude Desktop, and Windsurf, similarly addresses the fragmentation problem. Developers using multiple AI tools lose context with every switch, re-explaining decisions and repeating themselves constantly. AI security and vulnerability research. The security community has spent the first wave of AI risk assessment focused on model-centric threats: prompt injection, jailbreaking, data leakage. All valid, all insufficient. A paper titled System Security Foundations for Agentic Computing, highlighted in a widely shared analysis by Chris Hughes at Resilient Cyber, identifies where the foundational security principles that have governed computing for decades simply break down when applied to agentic AI systems. The most striking concept is what the paper calls the probabilistic TCB problem. In traditional security architecture, the trusted computing base, the set of components that must function correctly for security guarantees to hold, is deterministic. Hardware enforces that code cannot execute from certain memory regions. It works or it doesn't. Binary. In agentic systems, the LLM sits inside the TCB, and an LLM is fundamentally probabilistic. This isn't a bug to be patched, it's a category mismatch. 3 additional challenges compound the problem. First, security policies must be dynamic and derived from natural language task descriptions in real time, making the principle of least privilege, a cornerstone of system security since the 1970s, nearly impossible to apply when the privilege model changes with every prompt. Second, traditional guardrails operate at well-defined abstraction layers. Agents performing UI-level manipulations on the web don't have those clean boundaries, making security policies brittle. You cannot enumerate every safe URL. Third, agents process untrusted external content that can influence their behavior, functionally equivalent to dynamic code loading in traditional software, but without any of the sandboxing or verification mechanisms normally applied. The practical response to these theoretical challenges is taking multiple forms. Meta has released Secaline, described as the first fully open-source LLM with built-in model-level defense against prompt injection that achieves commercial-grade performance. The paper reports results across 9 utility benchmarks and 7 security benchmarks, finding that Meta Secaline 70B establishes a new frontier of utility security trade-off for open-source models and is more secure than several flagship proprietary models with prompt injection defense. Notably, despite being trained only on generic instruction tuning samples, SecAlign confers security in unseen downstream tasks, including tool calling and web navigation, suggesting that prompt injection resistance can generalize rather than requiring task-specific hardening. On the offensive side, Caleb Gross has published SIFT-rank, an algorithm that addresses what he considers the hardest unsolved problem in AI-assisted vulnerability research. Not detection, but prioritization. When automated tools flag thousands of changed functions in a stripped binary, the challenge is separating signal from noise. Traditional scoring approaches, including CVSS, suffer from score inflation where everything clusters at the ceiling. SIFT-rank instead samples small batches of approximately 10 items and asks an LLM to reorder each batch by relevance, keeping items that consistently rise to the top across many random comparisons. In a demonstration, it reproduced the discovery of CVE 2025-59534, a command injection in NASA's CryptoLib, in 45 seconds, ranking the vulnerable function first out of 286 candidates. Meanwhile, an agentic penetration testing tool is being iterated toward real target deployment, bundled into a single installable binary with two modes, YOLO, fully autonomous, and supervisor, directed assignments. Though it still struggles with OAuth authentication flows and CAPTCHAs, honest limitations that underscore how far automated offensive security still has to go. Claude AI and prompt engineering. The question of how Claude Code processes competing instructions, which file wins when Claude.md says one thing and a skill says another, has generated enough debate that someone finally did what engineers should always do: run the experiment. A team executed 1,007 successful trials across 12 experiment types, feeding Claude deliberately contradictory instructions from different sources and tracking which one the model followed. The cost was $5.62 via AWS Bedrock. The initial result seemed clear. Claude.md won 57% of the time, suggesting the global config has priority. But the researchers then did something most prompt engineering tests skip. They flipped the instructions, swapping which file contained which directive. The winner didn't follow the file. It followed the model's trained priors. The emoji experiment was the most revealing. Across 168 trials, no emojis won 100% of the time, regardless of whether the instruction appeared in the skill or the global config. Claude's trained behavior defaults to conciseness and avoids decorative fluff, and no amount of positional instruction hierarchy overrides that tendency. The takeaway for engineers is both liberating and humbling. Stop optimizing for where you put instructions, and start optimizing for whether your instructions align with the model's natural tendencies. When your prompt fights the model's priors, you are not configuring behavior, you are gambling on tokens. The finding also implies that the conventional wisdom about instruction priority stacks is largely a folk belief. What looks like positional priority is actually content alignment with baseline behavior. This finding connects directly to the security dimension of Claude Code usage. Rock Lambros's Zerg project, a parallel Claude Code orchestration system named after the StarCraft swarm strategy, addresses the fact that every major AI coding assistant was compromised last year. The IDSaster disclosure documented over 30 vulnerabilities across GitHub Copilot, Cursor, Windsurf, Claude Code, and JetBrains Junie, with 100% of tested tools vulnerable to prompt injection chaining through normal IDE features into remote code execution and data theft. Zerg's response is architectural. 3 isolation modes: task, subprocess, container, context engineering that cuts tokens 30 to 50% per worker, treating every token as a potential injection vector, OWASP security rules fetched from a trusted repository to prevent poisoned commits from degrading baselines, and pre-commit hooks that catch secrets before they reach repositories. Container mode runs workers as non-root with LD preload blocked, containing blast radius even if prompt injection succeeds. The insight that context engineering is security engineering is worth internalizing. Fewer tokens in a worker's context window means fewer attack surfaces, period. Anthropic's own latest report on agentic coding trends has prompted claims of prior art from practitioners who have been shipping similar architectures. Reuven Cohen argues that patterns now presented as 2026 predictions, orchestrator-centric multi-agent architectures, long-running persistent agents, human-in-the-loop escalation, shared vector memory, have been running in production since 2023 through his Claude Flow and RuVector systems. Whether that represents genuine prescience or parallel invention, the pattern is consistent. The industry is converging on orchestrated agent fleets with deterministic handoffs and explicit role boundaries, moving well past the single-agent copilot paradigm. AI theory and philosophical perspectives. Steve Yegge has never been one to bury the lead, and his latest essay is no exception. AI coding tools are vampires. Not metaphorical vampires in the sense of being parasitic. Yegge is emphatic that the productivity gains are real, estimating roughly 10x for developers who learn to use them properly. The vampire analogy is more specific. Like Colin Robinson, the energy vampire from What We Do in the Shadows, AI tools drain their users of vitality simply by being in the room. Yegge claims to have identified this pattern shortly after the new year, and has since watched confirming evidence accumulate. The core tension is economic. If a single AI-augmented engineer produces the value of 10 engineers, who captures that surplus? Yegge presents two extreme scenarios. In scenario A, the company captures 100%. The engineer works a full day at 10x output, receives no proportional compensation increase, makes colleagues look bad, and burns out. In scenario B, the engineer captures 100%, working 1 hour per day to match peers' output and coasting. But the company goes under because competitors with harder-working AI-augmented teams will eat them alive. Both extremes are unsustainable, and Yegge concludes that the answer must lie somewhere in the middle, or we're all pretty screwed. He pins a specific date on the inflection, November 24th, 2025, when Opus 4.5.4.6 and Claude Code represented a qualitative leap. As supporting evidence, he cites reports that Microsoft is openly encouraging employees to use multiple AI tools, with Claude Code rapidly becoming dominant across engineering at Microsoft. The addiction dimension is worth noting. The productivity gains are genuinely compelling, creating a cycle where developers push harder, produce more, and deplete themselves faster. The vampire feeds precisely because the experience feels good. The theoretical underpinnings of how to constrain AI creativity without killing it are explored in a research paper introducing generative ontology, a framework that synthesizes traditional ontological structure with LLM generative capability. The system encodes domain knowledge as executable pydantic schemas constraining LLM generation via DS-Pi signatures, with a multi-agent pipeline assigning specialized roles, a mechanics architect, a theme weaver, a balance critic, each carrying what the authors describe as a professional anxiety that prevents shallow outputs. The empirical results from the game grammar demonstration generating tabletop game designs are instructive. An ablation study across 120 designs shows multi-agent specialization produces the largest quality gains, fun d equals 1.12, depth d equals 1.59, p.001, while schema validation eliminates structural errors entirely, d equals 4.78. A benchmark against 20 published board games reveals structural parity but a bounded creative gap, fun d equals 1.86, with generated designs scoring 7-8 against published games 8-9. The framework generalizes beyond games to any domain with expert vocabulary, validity constraints, and accumulated exemplars, essentially the same logic floor concept from the agent architecture discussion, applied to creative generation rather than safety enforcement. A more speculative thread comes from Reuven Cohen's exploration of time as computational leverage, the idea that most systems waste cycles pretending everything changes every tick when reality is mostly quiet, then it shifts. The proposed approach, gate on causality and minimum cut, stay idle while coherence holds, spike compute only when structural boundaries break. Whether the framing of harvesting time at picosecond scales holds up to scrutiny is debatable. Commenters have pointed out that physical laws impose hard limits on the feedback loops being described, but the underlying principle of event-driven sparse computation has practical merit. A more grounded perspective on making LLMs predictable comes from Panta's walkthrough of pre-training processes, drawing on Andrei Karpathy's educational work, with the practical observation that good prompts alone are insufficient. Reliability requires architectural solutions beyond prompt engineering. Development tools and utilities. As AI coding agents consume increasingly enormous context windows and the tokens to fill them, the ability to actually see what's being spent in real time has shifted from nice to have to essential. TokenTap, published under the Sherlock repository, is a new open-source tool that intercepts LLM API traffic and renders a live terminal dashboard showing exactly how many tokens each request consumes, with a visual fuel gauge displaying cumulative usage against a configurable limit. It captures every intercepted request as both Markdown, human-readable with metadata, and JSON, raw API body for debugging, requiring no certificates or complex setup. Just clone, install, and run. The dashboard color codes usage: green below 50%, red above 80%, with a session summary on exit showing total tokens across all requests. The tool works by running as an HTTP proxy that sits between your terminal and the API, supporting Claude Code, Gemini CLI, and OpenAI Codex out of the box, with a generic TokenTap run command for anything else. In a landscape where a single agentic coding session can burn through hundreds of thousands of tokens, and where Claude Code sessions on AWS Bedrock are being explicitly cost-tracked, recall the $5.62 spent on 1007 prompt architecture tests, visibility into token consumption is a direct operational concern. The prompt capture feature doubles as a debugging tool. When an agent produces unexpected output, having the exact request body in JSON allows engineers to diagnose whether the problem is in the prompt, the context, or the model's interpretation. The broader testing and quality engineering landscape is undergoing its own architectural shift. Dragan Spiridonov's competitive analysis of 19 AI testing platforms finds that the single-agent copilot era, where an AI assistant fixes broken XPath locators, is already obsolete. The real transition is toward coordinated fleets of specialized agents, each handling a specific quality function. Chaos engineering, contract validation across microservices, security scanning within CI/CD, accessibility audits, test case generation from real user telemetry. Gartner reportedly tracks a 445% surge in multi-agent system inquiries from Q1 2024 to Q2 2025, yet none of the 19 platforms analyzed offers multi-agent fleet orchestration with open-source access. Most remain single-agent architectures with impressive demos and closed ecosystems. The uncomfortable truth is consistent across domains. The tooling has not caught up to the architecture everyone agrees is coming. Whether it's ternary model inference, agent security, or quality engineering at scale, the gap between what is theoretically possible and what is practically deployable remains the defining constraint.